In this video, we're going to go over section 6.1 and 6.2, and I'm going to suggest that you have StatCrunch opened before you start watching the video so that you can follow along with the normal calculator tool that I'm going to demonstrate during the video. So section 6.1 deals with the standard normal distribution, and we need some definitions first. So let's go ahead and take a look at a density curve. And a density curve applies to a graph of a continuous probability distribution. If you remember in the last chapter, we looked at discrete probability distributions. Now we're going to talk about continuous. And the continuous curve, or the density curve, has to satisfy the requirement that the total area under the curve is exactly 1. And because the area under the curve is 1, there's a correspondence between area and probability. So properties, the first one we're going to talk about in this section is the uniform distribution. And the uniform distribution, the area under the graph of the continuous probability distribution is equal to 1, as we just stated. And again, there's a correspondence between area and probability. And we're going to use the idea of a rectangle for the uniform distribution. I'm also going to show you another way to calculate the probabilities. You won't be using StatCrunch for these calculations. You'll do these by hand. So a uniform distribution is a continuous random variable that has a uniform distribution if its values are spread evenly over the range of possibilities. And the shape of that, again, results in a rectangular shape. So let's take an example. During certain time periods at JFK Airport in New York, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 5 minutes, as illustrated in the figure right below here. So if we see here, between 0 and 5, equally likely to arrive. And since we're having 6 units along here, actually 5 units, then in order to get the area here to be 1, the height of this rectangle must be 0.2, because 0.2 times 5 gives us an area of 1. And again, waiting times can be any value between 0 and 5. That could be something like 1.234567 minutes, whatever number you want to pick between 0 and 5 could be a waiting time. It's a continuous, any number in that range. And we can find probabilities here by finding the area corresponding to the region that we're interested in. An important thing, let me just go back here for a minute, is that the height along here, in order to get this area to come out, we're going to use the 1 over the range idea. And the range here is from 0 to 5, which means our denominator is actually going to be a 5. And I'll show you that in the calculations. So given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So at least 2 minutes would be 2 minutes or greater. And again, we can fill in the area here and figure out how much area this represents relative to the total area. And you notice here, this is, if we go here from 2 to 5, we get 3 units times 0.2 gives us 0.6, so the probability is 0.6. Now, another way to calculate that is to simply look at the line part of this diagram here. And the range in the denominator is the upper value minus the lower value, 5 minus 0. And then the area that we're interested in is 5 minus 2, which gives us 3 over 5, or 0.6. I'm going to suggest that you use this calculation formula rather than trying to draw a picture each time. So the probability of randomly selecting a passenger with a waiting time of at least 2 minutes is 0.6. So let's try another example, and this comes from your homework. A statistics professor plans classes carefully, so the lengths of her classes are uniformly distributed between 49 and 54 minutes. Find the probability that a given class period runs between 50.25 and 51.25 minutes. All right, so we think about what we talked about before. This is a uniform distribution, and the class times run from 49 to 54. So again, the range there would be 54 minus 49 gives us a range of 5. And we're interested in the probability that the class runs between 50.25 and 51.25, which is a distance of 1. So the probability that a class lasts between 50.25 and 51.25 is going to be, in the numerator, we're going to find the distance between those 2 time periods we're interested in, which is 1 minute, divided by the range, which is 5. So the probability that her class lasts between 50.25 and 51.25 minutes is 0.2. Now let's talk about the normal distribution. This is another continuous distribution, continuous probability distribution that we're going to use extensively in this course. And it's one that has a symmetric and bell-shaped curve We've talked about this earlier in some of the earlier sections. And here's what the graph would look like. At the center of the distribution is the mean. And then it's, again, symmetric about the mean. We say it's bell-shaped and symmetric. The mean, the median, and mode actually all fall right there in the middle. And the standard normal distribution is a specific type of normal distribution with a mean of 0 and a standard deviation of 1. And this harkens back to the empirical rule that we learned about before. Remember, 68% of the data would fall within 1 standard deviation of the mean, 95% within 2. And we can find areas using a table or technology. Now, we're going to strongly encourage you to use StatCrunch. It makes the problems much, much easier. There's some information here about the tables. I'm not going to really go over that because I'm going to have you focus on using StatCrunch. And so here's just a little summary. So cumulative area from the left, and you're going to see some of your homework have graphs that are shaded in like this. This is what we call the area to the left, or the probability that a variable, Z-score is this value or less. This is probability being between two boundaries. And again, StatCrunch can do this very nicely for you. So here's my first problem. Find the area of the shaded region shown in the picture, and they give me the Z-score that delineates that shaded region to the left. And we're going to use a standard normal with a mean of 0 and a standard deviation of 1. Now, again, I would urge you, if you can, have your StatCrunch open, and I'm going to go ahead and bring up my StatCrunch so we can do this alongside here. So we want 0 and 1, so I'm going to go to Stat, Calculator, Normal, and I want to bring this over here so you make sure you can see it. And if you remember our problem, let me drag this down just for a second here. We wanted the Z-score to be 0.26. I'm going to put that in this window right here. 0.26. I'm going to pull it up so I make sure you can see it. And we've got the standard normal here. We've got less than or equal to, and then we just did a compute, and there's my probability right there. And I've got the screenshots in the PowerPoint so you can also see them here for reference. And there's what we just saw. So the probability here is 0.6026, and we read that right out of the window here. So these are the Z-scores over here, and these are the probabilities or the area under the curve. Now let's do an application with a bone density test. A bone mineral density test can be useful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a Z-score. The population of Z-scores is normally distributed with a mean of 0 and a standard deviation of 1, so these test results meet the requirements of the standard normal distribution. A randomly selected adult undergoes a bone density test. Find the probability this person has a bone density test score less than 1.27. So again, I'm going to use my StatCrunch tool, Stat Calculator Normal. It will come up as default with a mean of 0 and a standard deviation of 1. And then I'm going to enter the 1.27 in the window here, hit compute, and there's my probability. And I notice that the probability that a person has a Z-score or a bone density test score less than 1.27 is pretty high, 0.8980. Now use the same bone density test, find the probability that a randomly selected person has a result above -1, which is considered to be in the normal range of bone density readings. So again, we're going to use the StatCrunch tool, but we want to make sure that we set the inequality now to greater than or equal to -1. So if you notice right here, there's a drop-down window in the tool. I don't know if you can see that. Hopefully you can. Let me pull up the tool for a second. I'm not sure that's showing up in the window. Go back up here. So we wanted this to be greater than or equal to, and I want it to be -1, compute. And again, there's that drop-down that I use right there. And again, with my screenshots, it's 0.8413. And then finally, we want to go between -1 and -2.5, which is an indication that the subject has osteopenia, which is indicating some bone loss. Now again, on the tool, and I'm going to go ahead and pull the tool up, there's a between option on the StatCrunch tool, which is really nice. If you notice, it's right up here. And we want it to go between -2.5 and -1 and compute. And so I get a probability of 0.1524. And that's a very nice option. If you were using the tables, you'd have to look up two values and then do a subtraction. It's pretty complicated. And so there's your answer there. The probability being between -1 and -2.5 is about 0.1524. So about 15% of people would have this test and come up with an indication of having some bone loss. A little bit of notation. The first thing you see here is the probability that a z-score is between two values, A and B. The next one is the probability the z-score is above A. And the last one is the probability that the z-score is less than A. Now, we want to find z-scores from known areas. So instead of me giving you a z-score and saying, what's the probability, what if I give you the probability and say, tell me the score that corresponds to that? And one thing we might be interested in finding is what's called a critical value, which is a z-score on the borderline that separates z-scores that are significantly low or significantly high from the rest of the information. And we write this as z sub alpha, and this denotes an area of alpha to the right. And we want to find the value for z of 0.025. And so in what you're going to do in StatCrunch, you're going to put the inequality greater than or equal to, and you're going to put the 0.025 in the probability window, which is right over here. And you're going to read the z-score that corresponds to it right here. And that happens to be 1.96, which is a common critical value that we use. And if you remember, when we worked on empirical rule again, 95% of the data was within 2 standard deviations, which is just about this 1.96 here. And let's do another example. Find the indicated z-score. So again, we want to find the z-score that has 84, about 0.8485 probability above it. So again, you're going to use StatCrunch. You want to make sure you change that inequality to greater than or equal to. I put the area in the window on the right-hand side, and then I hit compute, and I'll get the z-score that corresponds. And we notice that this is a negative z-score because we're less than the mean, and the area is greater than 0.5, which definitely, if we write it z equals 0, we would have an area of 0.5. And so our z-score there is negative 1.03. Now, this problem here, they first want you to sketch what they're asking. So the first thing you want to do is read the question carefully. It says, find the probability a given z-score is less than negative 1.26, and we want to pick which is the correct graph. Well, first of all, I can eliminate this one because this is a between problem. This one has the area greater than. This one has the area less than positive 1.26, and so the correct graph is going to be B. Now we want to go ahead and use the normal calculator tool in StatCrunch to find that probability. And following the same steps before, make sure you change the inequality to greater than or equal to, less than or equal to. And you'll get your probability here of 0.1038. The reason I like this, again, this normal calculator, is it shows you what the distribution looks like. All right, let's move now to 6.2, which is also using the normal distribution, but now we're going to use distributions other than the standard normal. And this is where we're going to convert from a normal distribution to a standard normal by creating what are called z-scores, where we take the value we're interested in, subtract the mean of the distribution, and divide by the standard deviation, and that will give us the z-score. It allows us to standardize any normal distribution to z-scores to the standard normal distribution. So basically here you're going from a non-normal distribution, non-standard normal rather, to a standard normal. Now, the importance of this would be, especially if you were using the tables to work the problems, not as critical since we're using StatCrunch, but still it's important for you to understand the relationship between any normal distribution and then the standard normal distribution. And then this tells you how to do it if you were going to go ahead and use the tables, basically. If you're using StatCrunch, you really don't need to make the sketches because StatCrunch calculator tool will do that for you. So here we have a problem with what proportion of men are taller than the 72-inch height requirement for shower heads. So heights of men are normally distributed with a mean of 68.26 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a shower head at 72 inches. This is a real world problem. So we're going to go to StatCrunch, and I'm going to pull up my StatCrunch tool, and we've got a mean of, actually, let me just show you the pictures. So we're going to enter in the mean of 68.6, the standard deviation of 2.8, and then we're going to put in 72, and we're going to go greater than or equal to. And you can see my output right here, 68.6, 2.8, and so it looks like a little bit more than 11% of men are going to be taller than 72 inches, and they won't find that design to be suitable. So therefore, perhaps shower heads should be put up a little bit higher so that more men find them comfortable. Now we can go the other way, which is again to find values from known areas. This is similar to what we did before. And again, since we use StatCrunch, we don't need to draw a drawing of it. So let's do this one, aircraft cockpit. When designing equipment, one common criteria is to use a design that accommodates 95% of the population. We have seen that only 46% of women satisfy the height requirement for the U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, we want to find the 95th percentile of the heights of the women. Assume the heights of the women are normally distributed with a mean of 63.7, standard deviation of 2.9. In addition to the maximum allowable height, should there be a minimum required height? If so, why? Okay, so I'm going to go into StatCrunch. I'm going to enter the mean and the standard deviation, and then I'm going to put 0.95 into my probability window here. And I notice again, I'm going to find the 95th percentile, and it falls at about 68.5 inches, or 68.47. So we see 95% of women are shorter than, that's about 6'8.5" inches tall. And that's reasonable because it's greater than the mean of the women, which was 63.7. A requirement of a height less than 68.5 would allow 95% of women to be eligible. That would be the minimum height requirement so the pilot can easily reach all the controls. There should be a minimum so the pilot can reach all the controls. Okay, let's do a between question now. Assume that adults have IQ scores that are normally distributed with a mean of 105 and a standard deviation of 15. Find the probability that a randomly selected adult has an IQ between 91 and 119. So again, we're going to use the StatCrunch tool. We're going to use the between option. So I clicked on between here. I put in my mean and my standard deviation. I put in the two values I want to be between 91 and 119, and I find my probability right here. So the probability that a person would have an IQ between 91 and 119 is 0.6494. Now we want to find the IQ value above which 95% of adults fall. So again, now I'm going to put 0.95 into the right window here, and I want to have greater than or equal to, so it looks like an IQ of 80.33, or 80, 95% of adults would have an IQ above 80. And then one last one, and this is from your homework in my stat lab. The length of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. Two parts. Part A, find the probability of a pregnancy lasting 307 days or longer. Okay, so here's what we want to find. Probability of pregnancy is greater than or equal to 307, and we have a mean of 268 and a standard deviation of 15. So again, I'm going to use my tool, and I just showed you the bottom part of the tool here. I put in the 268 and the 15, and I put in greater than or equal to 307, and so very few pregnancies are going to be greater than 307 days. Which is 0.0047 is that probability. Now the second part wants us to find the length of pregnancy that separates the lowest 3%, which identify premature babies, from the rest of the pregnancies. So now we're going to enter the 0.03 over here into the window for area and find the value on the normal distribution that corresponds to that. And we see here it's 239.78 or 79, which would round off to 240 days. So births from pregnancy lasting 240 days or less are considered premature by this criterion.